Good morning, everyone. We're going to go ahead and jump into electron configuration. This is going to be part 2 of our videos for electrons and atoms, and we're going to deal specifically with this idea, these strange symbols that you're seeing on your screen. Now, we find the electron configurations based on Schrodinger's model, so we're going to be tying back to the orbitals and the sublevels that we talked about before as we do this. So let's get started. Now, learning targets. By the end of these three, before the end of this presentation, you should be able to explain how atoms follow the 3 main rules when filling orbitals. You'll be able to write the longhand electron configuration for a given element, as well as demonstrate how to write the shorthand electron configuration, or the abbreviated version, based on the element that we're working with. Now, what are electron configurations? Well, we know what electrons are, but configurations are sort of like the arrangements. So it's telling us where the actual electrons are located based on the orbitals. Now, the 3 rules that we're going to use here are: first, electrons fill orbitals starting with the lowest energy level first, and then building upwards. 2, no 2 electrons can fill one orbital with the same spin, and we'll go into that a little bit more in class. And 3, for degenerate orbitals, or orbitals where there's multiple places where there's equal energy, the electrons will go in one by one before they double up and get a second electron. Now, these rules we're going to use as we work with each element. So just keep them in mind, and we'll come back to it. Now, in terms of the off-ball principle, think of it like this. If you go to, think of your favorite sports team. The best place to be is usually closest to the field or the court. So, in the same way here, the electrons will always fill from the lowest energy, the ones closest to the nucleus, first, and then as they build, they'll continue to go up and up and up. Now, this diagram may look a little strange, but what you're actually seeing is once we fill what's called the 1s orbital, remember we talked about each level having an s orbital, it's going to go through 2s, then from 2s to 2p, and so forth. This would be our off-ball principle. Again, electrons are going to be lazy. They're going to start at the lowest point first. Now, the electron configuration of an atom can be written in 2 different ways. It's sort of a shorthand method of writing the sublevels. What do I mean? If you look at the diagram at the bottom of the screen, you'll notice that it says 2p2. So in the 2p sublevel, we have 2 electrons. So we show energy level, the energy sublevel, the shape S, P, D, or F, and then the number of electrons that are actually there. And we can find this using our periodic table. Now, as we work on the periodic table, we're going to need to pay attention to a few things. 1, the period number that we're going to use here is what we're going to call N. So in period 1, that's row 1, we'll say that that's energy level 1, 2, 3, 4, and so on. Now, in groups 1A and 2A, and you're going to want to label this on your periodic table, we call those our S block because they have S orbitals filled. When we go 3A through 8A, that's all the way over to where we see boron, aluminum, and all those over to the noble gases. Those have the P orbitals filled. That group in the middle that we call the transition metals, that big block, we call that the D orbitals. And then if we have to go even further down to those 2 groups that are at the bottom of the periodic table, we call those our F orbitals, or our F block. Again, you want to label these on your periodic table so you can use it to study and get very familiar with how you'll use this information. So, based on that, we can use the blocks to actually see which sublevels are filled or being filled for a particular element. And this is sort of, again, showing you just what we talked about before. Now, when we're writing an electron configuration, we have to make sure that each of the electrons is actually represented. So if we're going to do something for iron, iron has a total of 26 electrons. So we have to fill these in increasing energy. So we'll start at our 1s, then 2s, 2p, just like going back to the diagram that we spoke about before. And we're going to show how many electrons are actually allowed in each of those parts. So as we fill each sublevel with electrons, we actually show how many are there. So we have for iron 1s2, in the 1s orbital there are 2 electrons. 2s, we have 2 electrons. 2p6, in 2p orbital we have 6 electrons. 3s, we have 2. 3p6, 4s2, and 3d6. Now, if you're thinking in your head, why is it that 4s comes before 3d? That's actually a very good question. It's all dealing with the amount of energy it takes to fill that orbital. And again, we're going to practice this a little bit more when we get into class. Now, again, the total number of the superscripts or the exponents has to equal up to 26. If it doesn't, that means we did something wrong and we have to fix it. Now, let's look at the sodium electron configuration. 1s2, 2s2, 2p6, 3s1. There's a way that we can actually shorten this by using what we call the noble gas configuration. Really, it's showing the noble gas that comes in the row before it, and then we're going to put the information that comes after that. So, the noble gas that comes before sodium is neon. So, we can rewrite it by first writing the symbol for the noble gas, Ne, in brackets. This represents our core electrons, and then we write what came after that, or what's represented after that, which is just the 3s1. So this still represents sodium in terms of electron configuration, but it's just a shorter, more compact way of doing so. Here's a diagram showing you the basic idea of what we will be looking at for at least the ending portion of each of our electron configurations. Now, as we look at this last little bit, again, just pointing out that neon here is representing our completes the 2p subshell, so this is why we're able to write it. We have the core electrons represented, and then the remaining electron is hanging out here by itself. Now, the electrons outside of that noble gas configuration, the ones that come after that point, are what we call the valence electrons. These are going to be the electrons that are on the outermost ring of the element, of the atom. When an atom actually undergoes chemical reaction, only the valence electrons are the ones that are involved. These are the ones that are highest energy, furthest away from the nucleus, and so they're actually going to require many times the least amount of energy to remove. The valence electrons are the s and p electrons, okay? So s and p electrons after we finish with what we call the core. So if we have s and p orbitals that are already filled, we don't consider those. We go to the other ones that are not being used at that time. Based on this information and looking at our periodic table, we actually came up with some ways so that we can predict how many valence electrons we're going to have. Now, the thing that you want to pay attention to is, notice in both of these examples that it says Roman numeral 1A, 5A, those types of things. You want to look at the ones that are going to say A, not the ones that say B. The ones that say B are transition metals and they change up on us. So we don't want to get confused with those. But based on the naming convention that we have, 1A, 2A, 3A, and so forth, that tells us the actual number of valence electrons that we're dealing with there. Now, for this, or at this point at least, is where we'll actually go ahead and stop this video for now. I'll see you in class. I know I gave you a lot to think about, a lot to work on. Any other questions you have, please write them down. If you need to review or rewind, please do that so that I can answer those questions when we get into class. Have a great afternoon, and I'll see you in class.